Right, good, beautiful evening again, guys. It's such a joy, such a pleasure to once again grace your amazing, lovely presence and to once again give you another lesson on functions, right? We are basically still dealing with hyperbola functions and we are enjoying our time, our stay with hyperbola functions, grade 11. So let's look at them. Let's dive in once again. So we are still doing grade 11 functions. All right, it seems like this is a standard time, round about 9-ish to do functions. That's pretty cool. All right, so I'm back. So we're gonna look at grade 11 functions. Good, beautiful people. We're still dealing with those. All right, very important. Very important functions. So let us just look at this as an introduction. We are given the function f of x is equal to 2x minus 1 plus 2. And our hope today is that we can be able to do hyperbola functions and then we can transition into exponential so that we can cover the concept of hyperbola and exponential functions in this live session today. So let's look at how far we can go with the hyperbola function, then we'll transition into the exponential function. So we have f of x equal to 2 over x minus 1 plus 2, and our first question is they want us to sketch the function. So let's see how we are going to go about that. If we are going to sketch the function f of x is equal to 2 over x minus 1, then what we do is we need to do the planning first, where we can actually check what do we have. So we have, for instance, 2 over x minus 1. This 2, what does it mean? A is equal to 2 means a is greater than 0, which means I am anticipating that with my asymptotes, my horizontal and my vertical asymptote, I'm going to have my function available in the first and third quadrant. That's the first thing. 2. What do I further need for my planning? I need my asymptote. So I need my vertical asymptote and the equation. If we're looking for the vertical asymptote, we are looking at the denominator, the expression in the denominator. It's x minus 1. That's the expression in the denominator, x minus 1. So that x minus 1, guys, we simply equate that to 0, the x minus 1 in the denominator, and then we solve for x. We get x is equal to 1. Yeah. So whenever you are at a loss as to how to get the vertical asymptote, all you need to do in the standard form of the hyperbola function, you simply go to the expression in the denominator, okay, and then you equate that expression to 0 and solve for it. So I repeat, you go to the denominator, go to the expression in the denominator, which is x minus 1. You equate to 0, solve for x, and there you will have your equation of the vertical asymptote. Then secondly, we need the horizontal asymptote. Our horizontal asymptote is represented by the constant term there, the positive 2, which is a standalone term. So the horizontal asymptote is y is equal to 2. All right. So those are two things: vertical asymptote, x is equal to 1. Horizontal asymptote, y is equal to 2. Thirdly, we need the x-intercept, and we know the x-intercept, it's where we let y be equal to 0. And we also need the y-intercept, which is where we let x be equal to 0. All right. So that's very important. Y-intercept is found on the y-axis. X-intercept is found on the x-axis. On the x-axis, we let y be equal to 0. On the y-axis, we let x is equal to 0. So then we go back to our function. There it is. And remember, this notation, f of x, simply stands for y. This notation there, f of x, it stands for y. So what then we do is we go to that f of x, we let y be equal to 0 there. So we're going to say 0 is equal to 2 over x minus 1 plus 2. You see? Hello, Karando, once again. Then we take the 2, the positive 2, we transpose it over to the left-hand side. We get negative 2, and we isolate the fraction 2 over x minus 1. And remember, we cross multiply the LCD. Okay, remember, because the concept behind all of this is that we find the LCD, we write the restriction, and then what do? We multiply both sides with the LCD in the numerator. But when we multiply with x minus 1 in the numerator for this fraction, the x minus 1 and the x minus 1 cancel, it leaves us with 2. So that's why we simply use the idea of cross multiplying, but it comes from a mathematical concept. So it's not something that's basically formed along the way. Then remember, we get negative 2x plus 2. And remember, our negative 2x, we transpose there on the other side, and we find that our x value, when we divide both sides by negative 2, we have x is equal to 0. Is equal to 0. If we were to write the coordinates of that, we would say it's 0, 0, of course, no problem. Then in the same vein, guys, we let x be equal to 0. We go to the function y is equal to 2 over x minus 1 plus 2. Remember, we said we're going to let x be equal to 0. So y is equal to 2 over 0 minus 1 in the denominator. 0 minus 1 gives us 2 over negative 1. Then 2 divided by negative 1 gives us negative 2 plus 2. Then negative 2 plus 2 gives you 0. Okay, so then obviously then that means our y-intercept is given by y is equal to 0, but when we write the coordinates, we write them as 0, 0. Okay, then when we are about to sketch, we note that, okay, we have an idea as to where, in which quadrant our function should be based on the a value. We were able to figure that one out because a is 2 greater than 0, meaning the function is found on the first and the third quadrant based on our horizontal asymptote and our vertical asymptote, because the quadrants are defined by the asymptote. It's grade 11, Aubago, but obviously relevant to grade 12 because grade 11 and 12, they have similar concepts when it comes to functions. Number 2, horizontal asymptote. We took the expression in the denominator, equated it to 0, solved for x, we get the vertical asymptote. Horizontal asymptote, we took the value of this constant term as it is in our general form of the hyperbola function, and we took it and basically said y is equal to 2 because the constant term as it is gives us the equation when we say y is equal to 2 of the horizontal asymptote. Then 3, we find the x-intercept and the y-intercept. To find the x-intercept, let y be equal to 0. To find the y-intercept, we let x be equal to 0. Then we do the mathematics, the algebraic gymnastics, okay, where we let y be equal to 0. So in the place of y, we write 0, transpose the 2, get negative 2, 2 over x minus 1 on the right. We cross multiply, negative 2 into 2x minus 1 into x minus 1 is equal to 2 into x minus 1 is equal to 2. We distribute the negative 2. We get negative 2x plus 2 is equal to 2. Take the 2 over, 2 minus 2 is 0. We divide both sides by the coefficient of x, which is negative 2, and that leads us to x is equal to 0. There we have it, guys. The coordinates of the x-intercept. For the y-intercept, we let x be equal to 0 for the very same function. We substitute in the place of x 0. There it is. 0 minus 1, 2. 0 minus 1 gives us negative 1. 2 divided by negative 1. Positive divided by negative is negative. 2 divided by 1 is 2. Negative 2. Plus this 2 gives you 0. Sorry about that, guys. Snizzles. So negative 2 plus 2 gives you 0, isn't it? So there it is. We have our y-intercept. And those are the coordinates. All right. Now, we can go and check out if we roughly go ahead and as we start to sketch our hyperbola function, we first sketch in the vertical asymptote, which is x is equal to 1. So 1 is here, vertical asymptote, there it is, x is equal to 1. Y is equal to 2. Y is equal to 2. Here, sketch in the horizontal asymptote. Use your ruler as you do so that you can see the sketch. You label the asymptotes. Okay. The equation of the horizontal asymptote y is equal to 2. The equation of the vertical asymptote x is equal to 1. Okay. Then, after sketching in our asymptotes, we've established the boundaries of the asymptote. First quadrant, second quadrant, third, and fourth. Now what's left now is to go to the x and the y-intercept. But fortunately or unfortunately for this particular function, the x and the y-intercept, they are the same. And the coordinates are the same. The origin is the x and the y-intercept. So we are expecting our function according to what we had said at the beginning. Since a is equal to 2 and it's positive, we're expecting our function to exist in the first and the third quadrant according to the asymptotes. So first quadrant and third quadrant. I already see the image of the function in my head because when I started I planned. Yes, it's grade 11. So this is my 1 point. And that point is basically the point for this arm. So please guys, when you sketch the arm, make sure you can see. Thank you, Makumbi. You're so beautiful, thank you. You make sure guys that you sketch your curve. All right. You see how the curve is. It's a nice, smooth, guys, smooth curve. Very nice and smooth. Can you see how smooth this curve is? All right. I usually suggest to my learners that for each arm, have at least 2 points. So I know this point is there because of the x and the y-intercept, all right, because they were both 0, 0. So that's why that point exists, and that's why I have it. But go ahead, try and maybe find another point. Let's say, let's check when x is -1. You go to your function, you go and substitute in the place of x when it's -1. Thank you, Bali. you substitute x as -1 here. So you have 2 over, if you substitute -1, you're going to have 2 over -1 minus 1 gives you -2. Plus 2, you get 2 divided by -2 gives you -1 plus 2. And ultimately your answer is 1. So when x is -1, you substitute x as -1, you get a corresponding y value of +1. When x is -1, substitute in the place of x -1, you get a corresponding y value of y being +1. Now, you see, that makes sense because 1 would be here and the -1 would be there. So do you see my curve? How nice and smooth my curve is. At least now I have 2 points for that one arm. And I usually recommend that at least have the 2 points for the arm so that you can see how the curve, how smoothly the curve curves, for the 2 points. All right, so at least have those two points for the one arm. Now remember, I said that this particular function will exist in the first and the third quadrant. Why? Because remember, we said a, meaning our numerator value, is +2, which means a is greater than 0, which means by virtue of a being greater than 0, we're expecting that the function will exist in the first and the third quadrant. So I know I have an arm that exists here. But look, if the arm exists here, it means it won't touch this line, it won't touch that line. So let us utilize then the other values of x after x is 1. So let's check at x is 2 and look at x is 3. You go to your function, go and substitute, man. All right, you can use your calculator quickly, guys. Like, you don't have to write down. You see, I wrote down because, you know what's happening with me at the moment? I don't have a calculator because, I kid you not, my kids at school, when they lose calculators, they come and they ask for a calculator from me. And then what happens is that my heart of generosity gets in the way and I end up giving away my calculator. Is equal to 2. So, calculator here. 2 over 2 minus 1. Obviously, 2 minus 1 in the denominator is going to give you 1. 2 divided by 1 is going to be 2. 2 plus 2 is going to give you 4. So when x is 2, y is what? So I repeat this thing. You substitute 2 in the place of x. It gives you 2 minus 1, which is 1. What's 2 divided by 1? It is 2. And then that 2 plus this 2 gives you 4. So that means when x is 2, y gives you 4. When x is 2, y gives you 4. When x is 2, y gives you 4. That's where they meet, these two. They meet there. So that's that point. Let's check when x is 3. What's the corresponding value of y? Why am I doing this, guys? I'm doing this because for the arm that is here, I need to at least have points so that when I sketch the arm, we can see the smooth curve, all right, of that particular arm. So I substitute x is equal to 3 here. Let's come in and substitute x is equal to 3 here. 3 minus 1 gives me 2. 2 divided by 2 gives me 1. 1 plus 2 gives me 3. So when x is 3, y is also 3. This there. Horizontally, this is there. Vertically, this is there. That's where they meet. So do you see these two? Now I'm going to play dot to dot. Guys, do you remember dot to dot from when you guys were back in like grade 1? And in mathematics, they used to have dot to dot so that you can actually follow. Now it's like we're casting back to dot, at least just for the 2 points that we need for that arm. So at least having 2 points for that particular arm, I can see the shape of the function in that quadrant. Look at it, so smooth. This arrow approaches this vertical asymptote, never touches. This arrow here, or this function this side, approaches this horizontal asymptote, but never touches. How important it is for individuals to be able to exist in a place without ever touching certain things. That day when young men in schools can refrain from touching a cigarette, whilst they have friends maybe or associates at school that basically touch cigarettes and smoke them. That day will be amazing. That day when young men refuse to touch young ladies so that something else comes about because of touching, and they basically create boundary lines, so that by doing that, what do? They retain their sense of identity as far as who they are. You see, even the function, the hyperbola function, it retains its sense of identity because it has these boundary lines. The function does not exist because if for a moment it tries to exist in those boundary lines, it ceases to exist, it loses its identity, and things go haywire. All right, so there, guys, that's how we sketch the function. Now I have some follow-up questions. All right, the follow-up questions after this is domain. They're asking me give the domain of the function. Okay, so remember, I've been able to sketch the function using the a value. When it's positive, it means first and third quadrant. If it was negative, it would mean second and fourth quadrant. Okay, so please, guys, the quadrant is always dictated by the a value. Vertical and horizontal asymptote, we spoke about. Then finding the x and the y-intercept, we spoke about. Then the other thing is the other points. Getting other points, all right, which is something that I just did. Getting the other points for the curve that has nothing. For the curve in the quadrant when nothing is actually found. Okay, where coordinates are not found. So you need to at least have the decency of finding those, right? I hope we get the point there. Thank you so much. All right, so guys, yeah, that is the equation of the vertical asymptote. It's x is equal to 1. That is the equation of the horizontal asymptote, y is equal to 2. You get the equation by identifying the constant term for the horizontal asymptote. So it's y is equal to 2 based on the value of the constant as it is. Then the equation of the vertical asymptote is based on the inverse of the constant term in the denominator. So if it's negative 1, it means the equation is x is equal to positive 1. It's always the opposite sign, opposite number of a constant term in the denominator. So let's look here. What is domain? If we are saying what is the domain of this function, the one that you have before me, this one, what would we say is the domain, guys? All right, let's see if my geniuses are here, people that know their stuff. Okay, by definition, remember, domain is the possible x values where the function is defined. Possible x values. And when we look at domain, we look at it from left to right. We slide through and check, does the function exist, not exist, exist, doesn't exist. So where does the function exist? From left to right. Exist. And probably why do you guys see me saying exist? The thing is, this arrow, you see this arrow? This one. It's like an infinite, it's an infinite affair where this arrow, this function in this quadrant, the hyperbola function in this quadrant, the arrow approaches this line, but never ever, there's never a point where it touches, but infinitely, it is always indefinitely approaching that line, but never touching it. So the function exists everywhere, all right, on the left hand side of the asymptote. The function exists everywhere on the left hand side of the asymptote. But on the asymptote, the function doesn't exist. Then the function exists everywhere on the right hand side of the asymptote. Do you see that, guys? So here, that's where the function does not exist. But domain is the possible where the function exists. So what we say is that we say x is an element of real numbers, and then we put a semicolon, meaning but x cannot be what? What is our vertical asymptote? It's 1, so x cannot be 1. All right, that's our domain. Then range, the range of this function. Remember, range speaks to the possible y values where the function exists. Possible y values where the function exists. So if we look at this function, as per the grade 11 and 12 syllabus, what would be the range of this function? The range is y. Remember, when we are looking at the range, we are looking at it from the bottom to the top. Bottom to the top. Everybody in life starts at the bottom to the top. When you are growing from a young age, you usually grow from short to tall gradually. All right, so bottom. That's why that song says started from the bottom, now we here. When you started from the bottom, you started from a very low point, but then you here. So we're always looking from the bottom up. So look at the function. Where does it exist? Exists, doesn't exist. Exists, you see? So basically this arrow here shows that the function approaches this line indefinitely. It goes on infinitely in that direction, never stopping, ever going, never stopping, ever going, never stopping, ever going. All right, so the arrow is an indication, never stopping, from the bottom. Okay, then here we stop, there is no existence. Then look at the function here. It goes up and away. Look at the arrow, it goes on infinitely in that direction, never stopping. So what does that say to you as far as the range is concerned? From the bottom to the top, where does the function exist? For all y values, the function will exist, meaning y is an element of R, but what? X, y. Why are you saying x? Okay, let's rub out this. How amazing is this pen, guys? Look at this pen. Look at this pen as it goes. Y cannot be, where's the asymptote? Y cannot be 2. Okay. Right. Some people usually, when they write the domain and the range, all right, they, instead of saying x is an element of R, they say x is an element of negative infinity to positive infinity with open brackets, right? And then they exclude the 1. X cannot be 1, right? So that's, I mean, that's an acceptable way to write the answer as well. Some people usually do it like this as well. They'll say infinity to what? To 1, but then there's gonna be an open brackets, and then you'll see this symbol or, and then it will start again 1 to what? Sorry, negative infinity, positive infinity, and they use these open brackets like this. So what do you see here? Negative infinity to 1, and they use open brackets because the 1 is not included. And then this here, this symbol, all right, means union. All right, this is just another way of saying or. All right, sometimes people write the word or they write union with this symbol that basically stands for union or. Okay, so negative infinity to 1, union 1 to infinity. This is another way that you could write the what? The domain of the function. So yeah, I'm just exposing you to various ways to actually do this, guys. You can do it in this way as well. All right, you know, just as long as maybe here you even say x is an element, and then you open those brackets, minus infinity to 1, open brackets, union 1 to infinity. And remember, we use open brackets because the positive 1 is not included as part of the answer. Okay, right, let's take it a step further. Look at something we didn't quite look at yesterday. Okay, the axis of symmetry for a hyperbola function. Okay, so first and foremost, what is the axis of symmetry? An axis of symmetry, guys, is something that basically what it does is it produces mirror images of the particular function that you are talking about. All right, It's almost as if like it kind of cuts the function into equal halves, if you will. So a hyperbola function typically has two axes of symmetries. And interestingly enough, those axes of symmetry, what they do is they actually, if I was to represent those axes of symmetry here in this particular hyperbola, this one, all right, the axis of symmetry would actually literally intersect through the point of intersection of the asymptotes. So we have here a vertical asymptote and a horizontal asymptote. So where the two asymptotes intersect, that is where one of the axes of symmetries, which has a positive gradient, and by positive gradient, remember guys that gradient has to do with the slope of the function. Okay, here we have an increasing function. Why? Because as x increases, y also increases. So from left to right, x is increasing, but from the bottom to the top, what's happening to y? Y is also increasing. Hence we speak about a positive gradient, slope, positive gradient, run over rise. Okay, or is it rise over run? Sorry, it's rise over run. So rise over run, change of y over change of x. So positive gradient, an increasing straight line that cuts through the point of intersection of the asymptotes. So this horizontal asymptote and this vertical asymptote here at this point are actually what? The coordinates are 1 and 3. Please take note, guys. The point of intersection of the asymptotes 1 and 3. All right, right? No, not 1 and 3. Why am I saying 1 and 3? Guys, why aren't you fixing me? This is positive 2. So it's 1 and 2. My bad, ne? Yeah. The x coordinate comes from the vertical asymptote. The y coordinate comes from the horizontal asymptote, because everywhere along this line, every point here, y is equal to 2. Everywhere along this vertical line, x is equal to 2 to 1. Okay, so y is equal to 2 everywhere on this line, x is equal to 1 everywhere on this vertical line. And the point of intersection of the two asymptotes is the point where the what? The positive gradient AOS. Positive gradient AOS. And that gradient, guys, will always be equal to 1 in the context of the syllabus from grade 10 to 12. So as a grade 10 to 12 learner, you need to know that the gradient of our axis of symmetry is either going to be, if it's a positive gradient axis of symmetry, gradient is always equal to 1. If it is a negative gradient axis of symmetry, and I want to say that we do have a negative gradient axis of symmetry, how does it go? It basically also does this, all right? But you see the slope of the function. This is a decreasing straight line. Why? Because as x increases, what happens to y? Y is decreasing. So as a negative gradient axis O of symmetry, we know that that function in grade 10, 11, and 12 will always be, the gradient will always be equal to -1. So you should never be at loss as to what is the gradient of our axis of symmetry for both the increasing positive gradient axis of symmetry, because it's going to be +1, and for the decreasing axis of symmetry, which has a negative gradient, because it's always going to be -1. No questions at all where that is concerned. And I'm sure you can see that this positive gradient axis of symmetry, you can see it basically opens, it presents mirror images. Look at the mirror image of this function opposed to this side. Bisects, cuts into half, have a mirror image on this side as well of this side. Do you see that? That's what the positive gradient x of symmetry does. Look at the negative gradient x of symmetry. It also gives us a mirror image on this side, a mirror image of this side on this side. Do you see that, guys? I hope you guys can see that. Okay, so that is the role of the axis of symmetry. All right, what you see on the left, you will see on the right. What you see on this side of the x of symmetry, you'll see on this side of the x of symmetry. Likewise, this side. What you see on this side of the x of symmetry, you'll see on this side of the x of symmetry. Hence, we talk about mirror images. Mirror images. Mirror images. Okay? All right? Now, how do we find the equation of the x of symmetry? Because finding the equation is something that we are usually asked. Okay, and remember, I told you there's a positive gradient x of symmetry and there is a negative gradient axis of symmetry. So your positive gradient axis of symmetry, right, as I said to you, our gradient, if it's the positive gradient x of symmetry, will be equal to 1. But our gradient for the negative gradient x of symmetry will be -1. So since we see that the x of symmetry is a straight line, and it always is, that means the form of the function is going to be y is equal to x ax plus q. That is going to be the form of the function, right? Because any straight line will have a gradient, which we know obviously will be 1 here in this case. And all that we are left to find is the value of the constant term, all right? Which, as I said, remember, we do have a point of intersection because of the asymptotes, which we are aware of, which we can use and substitute, all right? Because we can substitute those points into this equation to get the value of q and then find the equation, all right? So that's just something to note, guys. So if we can substitute the point of intersection of the asymptotes, what is the point of intersection of the asymptotes given our sketch here? Remember, our horizontal asymptote was y is equal to 2, so that means the y coordinate of the point of intersection is positive 2. Our vertical asymptote was actually x is equal to 1, which means that the x coordinate of the point of intersection is 1. So we have the points 1 and 2. So let's go substitute them. This is x, this is y, so this is 2 is equal to x, and then obviously the x value is actually, we are given the x value, it is 1. So let's say in the place of x we are going to substitute who? 1 plus who? Plus q. Then we solve 2 minus 1, therefore q is equal to 2. So what does that mean for the equation of the x of symmetry? Y is equal to, remember, our gradient, since it's the positive gradient x of symmetry, we established that it is 1. It always is positive 1 if we are talking about the positive gradient x of symmetry. So therefore our equation is y is equal to x. We wanted the q value, we got positive 2. Here is the axis of symmetry, the positive gradient axis of symmetry. It is equal to y is equal to x plus 2. Yeah, I'm crazy, eh? I'm very crazy. Do you see how crazy I am, guys? And do you see how inaccurate this nonsense that I've just written is? 2 minus 1 is equal to 2. And nobody picked that up as I wrote down. I'm misleading you guys, and you're allowing me to mislead you. Ha ha ha, you guys. You guys. Okay, so 2 minus 1, guys, is equal to 1. Therefore, that value, sorry, let me just erase this, because the q value is not 2, it is actually equal to 1. So there we are. Y is equal to x plus 1. That's the positive gradient x of symmetry. right? And so what's beautiful is that once I am able to get the actual equation, sketching this function is actually not something I can just assumedly do, but I know that it basically here, if this is 1, it means that this has a y value or y intercept that cuts through there. You see now? Now we are talking. Now we're talking. It is the x of symmetry. It has the y intercept, because remember, if this here is positive 1, then it means it must cut through the y intercept, which is 1. Now, it's proper. It's proper. Okay, let's go and find the negative gradient x of symmetry. I'm going to do the same thing. Y is equal to, remember our gradient is negative, so we're going to say negative x plus 2. Then what are we going to do? We use the point of intersection of the vertical asymptote and the horizontal asymptote. We use the point of intersection of the vertical asymptote and the horizontal asymptote. Okay, so let's go. The vertical x value is going to be 1. Y is going to be 2. So we use that point to go and substitute so that we can solve for q. So 2 is equal to negative x. Okay, remember our x value, sorry, when we are substituting, we substituted y is equal to 2 in the place of x, we substitute 1. And then we transpose the negative 1. 2 plus 1 equal to 2. Then 2 plus 1 is what? It's 3. Therefore, what is the equation? Y is equal to, remember, it's negative x plus the 3. Okay. And what do you see here? Y is 1. Y is 1 is negative. Y is 1 is negative. Slibo, Ohio, you need to help me out there. Y is 1 is negative. I don't know if I'm not understanding the question. Are you asking why is one of the axis of symmetries having a negative gradient and why is the other one having a positive gradient? Is that what you are asking? Okay, Liabona, it seems like he's asking. Oh, okay. So like I said, when I was starting off, when I was sketching, or when I was actually introducing the concept of the axis of symmetry. Remember, symmetry means a line that cuts so that we have mirror images of the actual function on either side. So like I said to you guys, I said that there are two axes of symmetries for a hyperbola. There is a positive gradient axis of symmetry. Okay, guys, this line is an increasing line. It cuts and it cuts through the point of intersection of the two asymptotes. We have this horizontal asymptote, which is y is equal to 2, and this vertical asymptote, which is x is equal to 1. This line cuts through those intersection of the two asymptotes. So where they intersect this asymptote, it's at x is equal to 1 and y is equal to 2. So there is a symmetrical line that cuts through that point of intersection. That symmetrical line is an increasing straight line. The direction of the straight line is an increasing straight line, meaning it has a positive gradient. Go back to when you did linear functions in grade 9, then in grade 10, now you are in grade 11. All straight lines that increase have a positive gradient, because as x increases from left to right, what happens to y? It rises, it increases as well. So this is a positive gradient axis of symmetry. And then because it is a positive gradient of axis of symmetry, we know that the gradient of any axis of symmetry within the confines of the grades 10 to 12 in the high school context, we will always have the positive gradient axis of symmetry have being m is equal to 1, or the gradient will always be positive 1. Not positive 2, never positive 3, but only one natural value or natural number, which is 1. And that 1 is positive. So our gradient is positive 1 for all axes of symmetries that have a positive gradient within the context of the syllabus that we are doing. Then we have another axis of symmetry, but that axis of symmetry, it also cuts through the point of intersection of the asymptotes, but it is not increasing in nature, but it is what? It is decreasing in nature. Why? Because as x increases, y does? The fall goes down, decreases. So this straight line has a negative gradient. It does not have a positive, it has a negative gradient. This axis of symmetry. Look at this positive gradient axis of symmetry, for instance. What does it do? It bisects the function so that we have this mirror image on this side, which is similar to this mirror image. That's what an axis of symmetry does. Look at this negative gradient axis of symmetry. It basically also ensures that on this half we have a mirror image, on this side we have the same mirror image of that one, just on this side. Therefore, that's why we are saying it is an axis of symmetry, but it is having a negative gradient, whereas this one is having a positive gradient. So when we go and find the equation, we must note that the gradient of the positive gradient axis of symmetry is 1. So therefore, in the place of where the gradient should be, we write positive 1. There. 1 is there, unseen and present. Okay, we're just showing it there. Then we use the point of intersection of the asymptotes to then go ahead and find what is the value of u by substituting these points. X is 1. In the place of x, we write 1. Y is 2. In the place of y, we write 2. Then we solve for q, which gives us 1. Therefore, our equation is y is equal to x plus 1. That is the positive gradient axis of symmetry. Moving right along, we go to the negative gradient axis of symmetry. The gradient is negative 1. We write the equation y is equal to negative x plus 2. We use the point of intersection where the horizontal and the vertical asymptote, they intersect. We use that point. We substitute y, which is 2. We substitute x, which is 1 in the place of x. So that means this negative and the positive 1 gives you negative 1. We transpose the negative 1, becomes positive 1. We solve for q is equal to 3. Then when we write the negative gradient axis of symmetry, it is equal to y is equal to negative, since it has a negative gradient, x plus 3. Slibo. I hope you're not sleepo. Slibo. I hope you're not sleepo. And I hope you have heard it loud and clear, my dear friend, who seems to come and go. All right, gotcha. I gotcha too. Right back at you, big man. Right back at you. Now, I want to look at another interesting question. So I hope now we are all clear about how to find the equation of the axis of symmetry, and therefore after finding it, how sketching it becomes easy, because if we write or draw the straight line y is equal to x plus 1, we need the x-intercept and the y-intercept of that function, right? So the x-intercept, that straight line cuts the x-axis at x is equal to negative 1 if you let y be equal to 0. And then if you let x be equal to 0, that function cuts the y-intercept at 1, but then there it is cutting or passing through the point of intersection, and there it is, the positive gradient x of symmetry, y is equal to x plus 1. If we want to sketch the negative gradient x of symmetry, we find the x and the y-intercept. We let x be equal to 0, which means y was going to be equal to 3. So what are we expecting? We're expecting that this function will pass through where y is equal to what? To 3. All right, we're expecting it to pass through there. There it is, really it is doing that. Then obviously the point of intersection, no doubt, it's going to pass through there, and then it goes on and cuts through the x-axis at some point. So in order to find out where it cuts the x-axis, we are going to let what? We let y be equal to 0. Then we solve for x. And when we solve for x, we get x is equal to 3, which means this function, okay, it deserves some redrawing. So I'm going to do that, because remember, in the beginning, I was just drawing it roughly. But now, since I have the equation, there's no need to draw roughly. I can represent the actual shebang. So this is 3, this is positive 3. So then what I do is I'm going to make sure that it's cutting through the point of intersection and the 1, I mean the 3. Okay. Yeah. So obviously you know it's not going to be this busy. You're gonna use the pencil, you're gonna be very neat, and it will materialize. So that's how we sketch the axis of symmetry. Please take note, guys. Take note, take note, take note, take note. So yeah, this is what I did there. All right, I know some people may feel that this is quite long, like, I mean, you're finding the positive gradient x of symmetry. All right, isn't there a quicker way? All right, let me just suggest as well that to find the positive axis of symmetry, there's also just another way where you write y is equal to, you write the brackets there, all right, to accommodate the denominator of the expression, all right, for your function. So you come here, look at this. You see this expression x minus 1, all you do is you go and plug it into this bracket. You see this plus 2, all you do is you come and plug it into this bracket. So since it's the positive gradient x of symmetry, we know that the gradient is going to be positive 1. So this is the form we are using. Y is equal to a into x minus p plus q. Here all you are doing, you are substituting what's in the expression in the denominator. Yes, you substitute it there. Here you write the gradient. So if it is the positive gradient x of symmetry, remember what did we say? We said that the value of the gradient is always positive 1. So you just write that there. Then the q value of the actual hyperbola function, which is 2, you just come and plug in that q in the place of 2. Guys, surely this sounds easy enough. And all you do is you play the distributive law. 1 times x, so you can remove the bracket, is x. 1 times negative 1 is negative 1. Then you have the plus 2 that you need to add. So our final answer for the equation is x is equal to plus 1. Now some people tend to feel that this method is much more quicker than all those gymnastics that I did here for finding the positive gradient x of symmetry. Okay, did you see what I did, guys? You just write this form, y is equal to a into x minus p plus q. You just go and fetch what the expression of the denominator, you substituted it there. Go and fetch this guy, x minus 1, go and substitute him in the place of this bracket, x minus 1. Then you go fetch positive 2, you substitute him in the place of q. Then your gradient a is positive 1, because for your positive gradient x of symmetry, your positive gradient axis of symmetry, you are always going to have a gradient that is equal to 1. So always in this grade, right? Because we have restrictive measures in place. Let's check how would we find the negative gradient axis of symmetry. Well, we would go about it and do the same thing. We just grab the form y is equal to a into x minus p plus q. Okay, then in the place of a, we write the gradient. Remember, since it's the negative gradient of x of symmetry, m is always equal to, or a is always equal to 1. Always. So we write in the place of a -1. Then we write x minus, remember we go and fetch. What do we fetch? We fetch the expression in the denominator. It's x minus 1. Then obviously plus q, we go and fetch the constant term, right? So the function has to be in this form in order for us to be able to fetch things. Go and fetch now the constant term. That's plus 2. And all we do, guys, is we distribute. Wow. So that means y, the equation y is equal to negative x plus 1. And then obviously that removes the bracket so that the 1 and the 2 can be able to deal with each other as like terms. So our equation is y is equal to negative x plus 3. Isn't that the equation we had gotten there through this method? Yes, sir. So guys, x of symmetry, is it difficult? Hi. It's delicious. It's beautiful to the taste, right? So that's what you guys should consider again, you know. So it's up to you which method you want to employ. You can employ this method, all right, which I told you, or you can employ this method. You must choose. Choose ye this day whom you will serve. This guy or this fellow? Who do you like? Option 2 or option 1? Which one do you want? Option 1, ladies and gentlemen. Option 2, ladies and gents. Which one do you choose? Choose wisely. All right. Okay. I see silence is golden. I wanted to look at this question. It says, give the equation if the graph is translated. If the graph is translated 1 unit upward and 1 unit to the left. Now this is a good question. Give the equation if the graph is translated. Translated speaks to movement or change of the function. Remember, the word trans is a prefix which means change. All right, so our function can change either by moving up or down, left or right. We can change the position of the function. So therefore we are given, remember we had been given the function y is equal to 2 over x minus 1 plus 2. Now what are they saying to us? If the graph is translated 1 unit upward, what does it mean when they say 1 unit upward? Who is affected? Who is affected? 1 and how? Hey, using those two questions, who is affected? So when we say 1 unit upward, who is affected? Who is affected here, guys? When we say 1 unit upward, who, first and foremost, let's start there. Who is affected? And then 2, how is he affected? All right. So if you look at this expression here, there are how many terms? There are 2 terms. there is 2 over x minus 1, which is one term, and then positive 2, which is the second term. And then in this one term, you have a numerator and the denominator. And here with this term, you just have this positive constant term, which is 2. So my question is to you, who is affected? Let's start there. When we say 1 unit upward, who is affected? Right? So hopefully we all know that up or down, whether we are moving up or down, he is affected. If it's up, then we know we are adding whatever units are there. If it is down, then we know we are subtracting however many units that we are asked to go down by. So what is happening, or who is affected? We know who. How? So this case is upward, meaning it says it translated 1 unit upward. How? By adding who? 1 unit. Where? Here to 2. So I know y is equal to 2 over x minus 1. We say plus 2. To this positive 2, we add 1. Because this here speaks to 1 unit upward. Because of that. Okay? So that's why we say plus 1. The second part says 1 unit to the left. So once again, we need to ask ourselves, who is affected? 2, how? So 1 unit to the left. Who, first and foremost, is affected? So we have a parameter here, which is the p-value, and he is affected. So in the denominator, who is affected? The constant term in the denominator. Question is, how? So now that's where we need to check here. If we say to the left, what are we actually saying? We say we are adding something. If we say to the right, what are we actually saying? We are subtracting something. To the left, we are adding. To the right, we are subtracting. That's why we usually say this here, everything that has to do with the p parameter, we say it is counterintuitive. Now I'm breaking down, I'm bringing in some big words here. That's why we say everything that has to do with the p parameter. In other words, the constant that is in the denominator. The constant that is in the expression in the denominator. The constant that is in the expression in the denominator. Everything that has to do with that constant, which is what we refer to as the p parameter. It is counterintuitive. What does the word counter mean? Counter is a prefix that means against. Intuitive means thought process or thinking process. So if we were to be honest with ourselves, the minute we head to the left, I'm sure some of you were not thinking plus something. What you were thinking is, if you are looking at the number line and we say to the left, we are looking at that and we are like, we are definitely subtracting something. But actually, what you are thinking is not what actually the reality is. It is counterintuitive. It is against your natural, normal thinking process. So therefore, when we say to the left, we are actually adding something to the p-value. If we say to the right, we are actually subtracting something from the p-value. So let's go back here and ask ourselves again. When we say 1 unit to the left, who is affected? Now I can boldly say he is affected. This is affected whenever we are talking about left or right, whereas he is affected whenever we talk about up and down. So let's check. -1 is affected. How did we say is affected? So if we say 1 unit to the left, it means we are going to add. Remember, left means we add however many units. So they said to the left by 1 unit. So it means we're going to add 1. Therefore, we can conclude and write the actual new function, because they said give the equation, the new equation. If the graph is translated 1 unit upward, who is affected? The Q value, we add 1. And 1 unit to the left. Who is affected? P is affected. How is he affected? We are going to what? Add, because we are saying to the left. When we are saying to the left, we are adding. When we say to the right, we are subtracting. So to the left, we add the units that we were told to the left that it's referring to. So the now final answer is y is equal to 2 over -1 plus 1. That gives you 0. So it means we are left with x alone in the denominator plus 3. Now, if you were to show a grade 10 learner this function, they would be like, now that is the hyperbola I know. Because this kind of hyperbola is the hyperbola that grade 10s are sketching, you know, very much so. Okay, guys, I don't know if anyone has any particular questions. Right, very good question, Kate. Kate, you're amazing. Thank you for asking that question. So Kate is asking in the comment section, if they ask the reflection of the equation in the x-axis, how are we writing the new equation? So Kate, listen up. Let us say we are given, I'm going to go back to that function that I initially had. Y is equal to 2 over x minus 1 plus 2. And let me just say that we were given the function as f of x is equal to 2 over x minus 1 plus 2. All right. Remember, let's first look at what a reflection in the what? In the x-axis means, first and foremost. And maybe what is the other way that this very same concept can be asked? Reflection in the x-axis, remember that the x-axis is the horizontal axis of your Cartesian plane, okay, denoted by the letter x, whereas your y-axis is the vertical line of your Cartesian plane, that is the y-axis. Now on the x-axis, the equation of this line, the equation of this horizontal line is actually what? Y is equal to 0. Why am I bringing this up, guys? It's because sometimes when they ask what Kate has just asked me now, if they say reflection in the x-axis, they may say to you, write down the new equation if it's reflected in the line y is equal to 0. Now people get lost in that moment and they're like, Haibo, what is that now? Because me, I'm used to reflection in the x-axis. Why are these people now asking me reflection in the line y is equal to 0? Wake up, sunny boy or sunny girl. These two things, x-axis, the line y is equal to 0, these things are the same. So I wanted to start right there just for us to understand what we mean by x-axis as opposed to y is equal to 0. Now the word reflection means mirror image. Mirror image. Are you with me? The mirror image of the function. Okay? Reflected along the line y is equal to 0 or the x-axis. So when that is the case, what are we doing? When we are talking about the reflection on the x-axis, it means there are important things that change and other things that stay the same. The question is, who changes between x and y? Between x and y, if we are reflecting in the x-axis. And I want to say that the person who changes between x and y, it is y. Y changes. Y changes. Y changes. So when we are reflecting in the x-axis, who changes? It is y. Or if we use the wording reflection in the line y is equal to 0, remember that the line y is equal to 0 is the x-axis. Therefore, who changes? Y changes. All right? Y changes. But x stays the same. Hey bana. Hey baba. Yo guys, I feel like when you get asked this question again, it is not a matter of doing what? Of engineering. I don't know what engineering is, but just simply recalling from memory. You know, I'm trying to help you guys understand that the x-axis is the line y is equal to 0. So if you are reflecting in the x-axis, you are wanting to see the mirror image on the other side. So if this is the x-axis, you want to see the mirror image on the other side of the x-axis as opposed to this side. You see, if it's this side, you want to see it on this side because you are reflecting along this line, the x-axis, you see. So in doing that, who is changing? Okay, who is changing? All right, remember, if let's say something was here, all right, and then it reflects and comes this side on this side of the x-axis. As you move this thing, all right, what is happening? Who is changing? Y was a certain value because y here is positive, but all of a sudden when you move this side, y is no longer positive, but y is negative. Hence we are talking about who is changing. Hey, y, all right, it's y. The thing is, Kate, you are lost because you don't want to understand the concept first before you utilize coordinates. I'm going to the coordinates, but I need you to first understand who is changing, because you need to look at reflection in light of what it means for the function. All right, yeah. So for that function, who is changing? So first and foremost, you need to understand this. Reflection in the x-axis, who's changing? Y. Okay, all right, y is changing, but x on the other hand is not going to change. All right, because there's only one person who's changing, it is y, but x is doing what? X is staying the same, guys. X is staying the same. X is staying the same. So firstly, let's look at the equation. If I had an equation, I was given the equation y is equal to 2 over x minus 1 plus 2. All right. Okay. So let us go back here just before I go to the equation. So in other words, okay, my good friend Kate, if we have here negative 2, this point, negative 2 and what? And 3. And I say A, all right, an image is formed. An image is formed that is reflected along this x-axis. Then the question is, what are the coordinates of A, the image that is formed through reflecting in the x-axis? The question is, what would be the coordinates of the image of A? Remember, if it's reflection along the x-axis, who did I say changes? Who changes? Y is going to change. So that means since y for a was 3. What is going to be the y coordinate for the image that has reflected x? Who changes, guys? Y changes. It becomes -3. Hey, Kate is saying -2 and 3. Hi, Kate. Okay, we are given a, which is -2 and 3. Then I say a, the image of a is reflected in the x-axis to give me the image of a. What is the image of a? If a reflected in the x-axis, who changes if we reflect in the x-axis? It is y. So therefore the new y coordinate for the image, which is formed by reflecting a in the x-axis, the coordinate that will change, or the variable that will change, is going to be y. Y from being +3 is -3. But the x value, guys, won't change at all. It is staying the same. Now, in light of this point, guys, you should understand that indeed, look at this. Underneath the x-axis, how are the y values here? Underneath the x-axis, the y values are negative. Whereas above the x-axis, how are the y values? The y values are positive. Okay, so who is changing when we reflect in the x-axis? It's always y that is changing, right? But x, Corey, x stays the same. Corey, x will stay the same. It will stay the same. All right, so this is reflection in the x-axis. Please understand that. Kate, are you with me? So now I hope it even makes more sense if you look at it in light of the coordinates. A was the point. The image of A is formed by reflecting in the x-axis. What would be the new coordinate? Reflecting in x-axis. The image of A formed by a reflection in the x-axis. A was -2 and 3. The image of A will be -2 because x doesn't change, but y will be -3. Now, what about the function? If we are given f of x is equal to 2 over x minus 1 plus 2, let's say for instance, and then we say the function f reflects in the x-axis to form g of x. What is the equation of g of x? F of x is this function, and then we are told it is reflected or reflects in the x-axis to form g of x. And the question is, what is the equation of the new function g of x? Right? So the concept is still pretty much the same. What are we saying here? Reflection in the x-axis means what? Y changes. Right, Kate? Something changes. So you can definitely, please try it. Okay, you are the one that asked anyways, the reflection in the x-axis. So it's only right that you be the one that tries it, and you'll be the one that takes it down, and you'll be the one that does the thing, and you'll be the one that is the one. The maths is mathsing, and you are mathsing, and hopefully everything is beautifully coming together. Because this is directly saying that y changes in psi. Then after that, we are going to divide or multiply both sides by negative, because we want to get rid of this negative at the end of the day. Remember, when we do that, we are going to multiply by negative for each term in the equation. So that means we are going to then have Going to multiply all of this by negative. That gives us negative 2 over x minus 1. And then we multiply this positive 2 as well by a negative. So that becomes negative 2. So therefore, that is the function of g of x. G of x is equal to negative 2x minus 1 minus 2. Network is not networking. It's killing me softly with network vibes. Is the network better now, guys? Okay, just again, let me just repeat that, because at this point I wanted to explain the whole reflection. Okay, reflection along the y-axis. Okay, so reflection along the y-axis can also be referred to as the reflection along the line x is equal to 0. If they don't say reflection along the y-axis, another alternative way of asking or stating the very same thing is a reflection along the line x is equal to 0. Hopefully we understand that now. So please, the line x is equal to 0 is a vertical line. The y-axis is that very line. All right, then who changes? So once again, who changes if we are reflecting along the y-axis? My network is really not good today at the moment. I don't know what's happening. It's not getting any better as well. Who changes? X changes. Y stays the same. Who changes? X changes. Who stays the same? Y stays the same. All right. So let's look at that point. I think Kate has really now hammered in this whole idea of, let's look at it in light of the coordinates. Let's say we had the coordinates negative 2, and it seems like negative 2 and 3 are very famous. Remember now, if we are reflecting along the y-axis, we are no longer going to be looking at the image down there, because that would be reflecting along the x-axis. We are looking at the image on the other side of the y-axis, which is also the line x is equal to 0. So we say, what is the coordinates of the image of A if A reflects along the y-axis? What is the image of A if A reflects along the line x is equal to 0 on the y-axis? So our coordinates would be what? Kate A. I'm waiting for Kate. Kate will help me out there, because Kate is Kating. Oi, Katie. Oi, Katie. Kate is Kating. Oi, Katie. Oi, Kate. Kate is Kating. Hey, look at Kate, eh? Doing the things. Riole Bocha as well, doing things. Riole and the kites, they are kating and rioling. Okay, right, so there it is, guys. Who's changing? He's changing negative 2 and becoming positive 2. Thank you so much. Yeah, I know you did reply. Good job. Very proud. I saw it. You that's why I'm saying Kate. Or unless like you just is the accent missing you there, and you're thinking it's not, I'm not saying your name right. And then y stays the same, Lilita, you see. Okay, and in the same vein, guys, if we're able to write coordinates, we should be able to write the function. So remember the function that I had. What if they said, what is the new function? Let's say this time h of x if f of x is reflected along the y-axis. What new function of h of x if f of x is reflected along the y-axis? So remember, what was the equation of f of x? It was y is equal to 2 over x minus 1 plus 2. So if we are reflecting along the y-axis, who's changing? It's x, right? So we say y is equal to 2 over this x value, we write it as negative x negative 1. Okay, and then we write this plus 2. Okay, but now remember, this negative sign, we don't usually have it being in the denominator. So what we do, we become smart about it. In this denominator, because it's a hyperbola, we take out a negative sign. We factorize, in actual fact. Take out the negative sign, we are left with x plus 1 in the denominator. Does that make sense, guys? You take out the negative sign, we are left with x plus 1. Then what do? You say the following: what is a positive divided by a negative something? Because remember, when you put the brackets, this makes it one term in the denominator because of the brackets being around the x plus 1. Then you say, what's a positive divided by a negative? Since that negative is acting as a coefficient of the bracket. So you say, what is positive divided by a negative? So obviously that gives you y is equal to negative 2 over x plus 1 plus 2. Guys, that means h of x, because remember we were supposed to write down what h of x the function is. So we say h of x is equal to negative 2 over x plus 1 plus 2. Okay, sure. Yikes. Now that was maths and a half, guys. Maths and a half. Okay, because remember I just said the new function h of x. What is the new function h of x? If f of x is reflected along the y-axis. So that means we need to write that function y is equal to 2 over x minus 1 plus 2. Okay, then we go ahead and we write y is equal to 2 over the negative x minus 1. We take out the negative sign. We write x plus 1 because we're factorizing. We're taking out the highest common factor, which is the negative sign of the first term. We're left with x plus 1. Add the 2. Then the positive divided by negative gives us a negative something, 2 over x plus 1 plus the 2. And then that's our function. Okay, yeah. So guys, simple, easy, straightforward, nice. That is also how we go about looking at reflection. I think for tonight I'm going to hold it right there. I don't want to over bombard us with concepts, but guys, this should give you an increased added amount of confidence to approach hyperbola functions. So what you can do for me is you can actually screenshot this. You can do it. You can also check out, there's the function, it's given there. F of x equal to negative 6 over x plus 2 minus 3. We want to know how to sketch the graph of f. Write down the equation of the vertical asymptote of f. Write down the equation of the horizontal asymptote of f. Write down the domain of f. Write down the range of f, and then determine the equations of the axis of symmetry of f. Okay, yeah. So by doing that, guys, we can just slowly but surely, solidify our understanding of these functions, so that at the end of the day, okay, we can be able to do this effectively, efficiently, and in the most accurate way possible. Who's this? Jules. Jules, I have no answers for you where that is concerned. I have no idea. What part 2? Can I ask what part 2 of functions investigation has? Yeah, I don't know. I don't know, Jules. I think Jules is asking about the investigation, and I don't know. It all depends on the particular school that you're in, because different schools are doing. Some schools are doing provincial investigations, if you want, but I don't know. It depends on where you at. Some schools are doing assignments. In fact, sorry, grade 10, 11, and 12 for CAPS. People are doing assignments, not investigations, if you are in grade 10, 11, and 12. Investigations are only being done for grade 9s and grade 8s, I believe. Okay. Gladys, what now? What about calculus? Look at this. Gladys is like complaining like insanely here. What calculus? What do you want? What do you need about calculus? You must tell me what aspect of calculus you want. You want us to take calculus from the beginning and move with it, or what? Gladys. Sorry, someone asked earlier on, do you have online classes? Kate, I do, but you'd have to contact me on the side about that, so that we can specifically talk about things. So for instance, there's someone yesterday that the day before yesterday that actually asked me about online lessons, and I was like, well, we can do that. Then I let them know about the online lessons and recommended that they can definitely also get the opportunity of like, the thing is, guys, there's something else that I do. Okay, please. I have 4 for what? Yeah, so we can definitely talk about it on the side, those people that want online. Okay, let's just speak on the side. Jules, what grade are you in? Quite, Jules. And why do people put white people's faces on the certified Jules, trying to get good grades? People are putting on white people's faces. Yeah. Oh my goodness, the only tricking thing about calculus is the optimization. Tabiso series says tricking. Yeah, the thing is, optimization has basic and then it has complex. Okay. Yeah, you can, Billy. You can do. Maybe you can add an additional question that's 7 and 8. Write a 7th question and say, Billy V, like I said, please contact me on the side. I'd love to just talk to you or chat to you on the side about that. Because you see, the thing is with that one, I also have like something else that I actually do that's added on the whole online thing. Because I think people think about online and they think about having a lesson and going ahead and having someone teach you, and that's one aspect of it. The thing is, there's another dimension that I add on it personally, and I think that other dimension or aspect is the one that basically I'd love to then have a chat to you about, because online classes can actually be they can be positive and a positive experience, or they can be a negative experience, and I think it also depends on what you do with it and how you actually facilitate it and actually go about it, and what other aspects do you add on to ensure that it is as effective and as positive experience for the individual, but also ultimately that it can actually serve its purpose, which is all people that want to have online classes. What do they want to do? They want to elevate, they want to level up and attain sweeter marks. Don't we all want to do that? People want to move from level 6 to 7. Some people want to move from level 7 to 8. Some people want to move from level 8 to cloud 9. Some people want to move from cloud 9 to outer space. You know what I mean? So it depends. The part where you have 4 equations. What are you talking about? Gladys. part where you have 4 equations. What in the world are you talking about? Gee whiz. Sure. Tavis. Yeah, you guys are talking about specifically. It seems like optimization is the pain of the day. Yeah. Well, you guys need to allow me to prepare for it. No, I don't do, Kate, I don't do physical science. That is an aspect I'm going to introduce in my online classes next year. All right. Some people have said to me they want help with Maths Lit. So that's an aspect I'm going to venture into next year. And then also some people have said they want help with physical science. So for now, guys, I'm not offering physical science, no assistance this whole entire year. So just make sure you never ask me again, just in good spirits. Yeah, gravitate towards individuals that can assist you and help you in that endeavor. Me, I'll be cooked, ready to serve you dinner next year, and it will be effective, you know. With the maths, we can cook. Yeah, we can cook that one. Yeah, so let's check it out tomorrow. We'll hop on to the whole what is it called, optimization. Actually, let's say we'll start with calculus tomorrow with you guys. We'll take it from the beginning with limits, the concept of a limit. Okay. Yeah, so we'll take it up, concept of a limit, then go into first principles, derivation using first principles, finding the derivative using first principles, take it up to differentiation rules, take it up to tangents, you know, tangents, how to find the gradient of a tangent, how to find the equation of the tangent, take it up to cubic functions. Guys, cubic functions are also key, cubic functions, and there's a whole host of things under cubic functions that you guys need to be able to also master and do very well. And then move from there, we can go on to optimization. All right, so it may, most likely it will take a few sessions for us to get through that, but we will definitely finish. Okay. Yeah, no, definitely, there's definitely merit. That's why most of my learners, some of them that are in grade 11, are killing the maths at the moment, because we started in December with the kids, some of them, when things were not so at the beginning. And I loved what happened with some of them in term 1. It's so beautiful to see, like they're getting 90s. And then now with term 2, like I can see some of them are just moving very nicely, you know, especially those that are very closely knit with, and we've had sort of like an ongoing interaction and communication since December. Some of them, yeah, since December end of the year, just before like Christmas and New Year's and so forth. Some grade 9s that I started with in December as well are doing phenomenally well this year, which is so cool to see. So when they started early, obviously it put them above and beyond. And I can remember the criticism I was getting from people just generally, like, why are you doing maths in December? Let the people enjoy. Now those kids are enjoying their marks, and some of people are crying who are basically giving me grief and pain, and who were never ceasing to come into my comment section and tell me, guys, you need to really like calm down. The year hasn't begun. I'm like, what in the world, guys? Don't people know that if you fail to plan, you are planning to fail? And I love those kids and the attitude they had then, because it's actually paid great dividends. So they're enjoying the fruits of that. I was checking out one other kid in the group that I have for grade 11s, and just helping out with the Euclidean geometry, like jumping from one question to the other. Nothing. Yeah. Is it Slibo? Now that's what I'm talking about. Now I love it. No, man, that's beautiful. These are some of the things that I really love. Thank you, guys. I really appreciate the feedback. Some people have contacted me via my YouTube, and they've let me know that, yeah, the live lessons have helped a lot, and I'm really glad. I'm really grateful that you guys give me the feedback, you know. Yes. it really means a lot. Oh, it means the world. So I was saying, guys, please additionally add question 7 and 8. Something about finding the equation if f of x is reflected in the x-axis, and then the next one you can write the equation of f of x if the equation if f of x is reflected in the y-axis, so that we can see the application of that reflection, all right, which we had spoken about. Okay, please guys do that. And then 6 says determine the equations, all right, plural, not one, but the equations of the axis of symmetry. So yeah, I'm hoping you guys can answer those questions, and we'll definitely be extending it as we go along for the grade 11s. Like, this is just obviously we're still just getting into the swing of things, with more interpretation questions with functions that we are going to delve into and we're going to check out, so that we can become more fluent in those as we go along. But thank you so much, guys, such a joy. Jules saying I got 93, and that was me. My teacher did not teach. Jesus. Jules, what grade are you in? Are you in grade 11 or 12? Yo, wow, that's amazing. Keep it up. Now, there's definitely people that work hard like that. Look at Jules doing the most. Jules, who are you, actual fact? Like, because this profile picture of yours is deceiving, so deceptive. I don't know if you are the white girl in the picture, or you are just Jules, sort of like this is your TikTok sort of like persona in the forefront, but you're just hiding behind that white girl persona there. I don't know what's happening there. So in grade 11, amazing. I keep it up. Grade 11 is such a joy. Grade 12, guys, is such a joy as well. It's such a joy when your grade 11 is solid. Okay, so if you're getting 93% in term 1 already, then please, guys, go ahead and do the most. Are you, Jules, are you a black African, or are you a white African? That's what I'm trying to establish here, because you are deceiving me with your profile picture, man. You know, guys, you know the whole thing about first impressions last. You look at a profile picture and it's almost as if that's the person that you're seeing. So no, that lasts. Okay, guys, let me love and leave you. Thank you so much. It was really a joy. Such a joy. I love this. I love doing this. You guys must know that I love doing this. I absolutely love it. I love serving people like this. It's a joy for me. No, like, yeah. It's a joy for me. Jules, I'm a black African. That's fine. Okay. Guys, we'll see each other again. Cheers. Thank you so much. And yeah, it seems like I'm checking out there. Gladys, it seems like you are it seems like Gladys is having insomnia. Please send your enthusiasm for maths to my teacher. No, Jules, man. No. I think you can rub it off on your teacher. Yeah, you can rub it off, I'm sure. Okay, guys, thank you again. Let's see each other again. Today I hopped on at 9 o'clock specifically. We'll see how the day goes tomorrow, guys, because sometimes it's just that other commitments get the better of me, and that's why you will never sometimes see me on the live. But I'll try tomorrow to hop on at an appropriate time. But let me love and leave you. Please, good night, and thank you again. You guys have been great sports. Cheerio, sleep well, night, everyone.